Hello, my name is Daniel Grimmer. I'm a graduate student studying philosophy of physics at the University of Oxford. I'm at Rubin College. This is a talk I gave yesterday at the Philosophy of Physics graduate lunch, but it wasn't recorded, and so I'm going to give it again today, recording it this time. I'll be talking about the pragmatic quantum field theory problem, which is an offshoot of the quantum measurement problem, and I'll talk about how two detector models for quantum fields can help us solve some of the issues I'm raising today. So first, I'd like to give an overview of the main claims I'm going to make in this talk before motivating them and laying out a roadmap. So claim number one will be that explaining all but maybe a small corner of quantum theory's experimental success unavoidably involves quantum fields, and in particular modeling parts of our measurement apparatus using quantum field theory. Claim number two, without a satisfactory understanding of how to model measurements involving QFTs, we would be at risk of losing the whole of quantum theory's evidential support, not just for quantum field theory, but for the whole of quantum theory, if quantum field theory is so experimentally important as I'm claiming it to be. Right. Claim number three is that textbook models concerning measurements of quantum field theories are very hand-wavy, and ultimately they're deeply unphysical, and fixing this is going to require QFT-compatible models of our detector systems. Luckily, there are two state-of-the-art detector models being used today for this purpose, the Unruh-DeWitt detector and the Fuster-Virch framework, but are these enough to restore the evidential support and physicality to quantum theory that I'm saying we're at risk of losing here? So, first I'd like to outline the scope of the talk. I'm saying we're dealing with a portion of the measurement problem, or the quantum measurement problem, so let me clarify what I am and what I'm not talking about. Despite quantum theory's remarkable success at predicting the statistical results of experiments, many philosophers worry that it nonetheless lacks some crucial theory-to-experiment link. I think there's various dissatisfactions with various theory-to-experiment disconnects which deserve the title the quantum measurement problem, so I view this term quite liberally, but they all center around the question, how are we supposed to model or understand the measurements of quantum systems? But exactly which of these measurement problems am I concerned with here? I'd like to make a distinction between pragmatic worries that you might have about this situation and realist worries. Pragmatic worries are along the lines of, how exactly are these statistical predictions supposed to be pulled out of the theory? How exactly should the measurement process be modeled? Right? Contrast that with more realist worries, such as, how could the world be such that my experiments have these statistics? And what explains the definite outcomes I see in each seemingly identical run of my experiments? I'm not satisfied with statistical predictions, I want definite predictions, right? I count that as a realist worry. And these all center around, how exactly should the measurement process be understood? You want some sort of realist narrative underlying your experiment and your models. I think both questions are very interesting, but the first one, in my estimation, is more important, since if it's unanswered, its consequences are more severe. So I'm saying the consequences are severe. What exactly is at stake here? Well, I think it's debatable whether or not a physical theory needs to provide us with a realist narrative. I know lots of people think we need this sort of thing. Other people think we don't. There's very intelligent people on both sides of it, and they've both got fair points, right? So that's at least debatable. Something which I think is much less debatable, or not debatable at all, is that a physical theory needs to provide us with a robust account of how predictions can and should be made from it. If you don't have a way predictions for very specific, realistic experimental scenarios which are actually performed, right? It's that makes a physical theory physical, the connection with actual experiments. Right? Without that sort of robust account, we're at risk of losing any right to claim evidential support for the theory in question, or worse, its physicality. To claim evidential support, you really have to do a lot of modeling within your theory to connect with the particular exact real-life experimental practices which produce data which you're claiming support your theory. Right? Something I'd like you to take on faith for now is that for non-relativistic quantum mechanics, These pragmatic issues I'm worried about are mostly solved, I would say, very satisfactorily, in terms of measurement chains and the Heisenberg cut. Take that on faith for now, but also take on faith that for quantum field theory, we have big trouble ahead, and this is quite an issue for us. And I'll get to why that's the case later on, but take that on faith for now. So, what's the scope of the talk? I'm going to be neglecting the realist portion of the quantum measurement problem entirely. And so rather, I'm going to say, let's first work on bringing home the spoils of our experimental success, and then let's worry about what it all means later, right? And keeping up with this, so here's an outline of the talk. I've already talked about what part of the quantum measurement problem we're dealing with here, this pragmatic version, in particular the version centered around QFT. Now, keeping up this metaphor of bringing home the spoils of experimental success, I'd like to next discuss where were these spoils won? Is it mostly in terms of quantum field theory, or is it mostly in terms of non-relativistic quantum mechanics, right? So in which camp do most of the experimental spoils lie? Then I'll talk about what blocks their way home. Why don't the textbook models of measurement in quantum field theory work? And what are some fundamental issues we run into there? In part 4, I'll talk about how two detector models, which are built to be compatible with QFT, the Unruh-DeWitt detector and the Fuster-Wirtz detector, I'll introduce these and contrast them. And then in the last section, I'll talk about measurement chains and cuts and see how these things can help us explain the issues that I'm going to be raising throughout this talk.